Good day and welcome back to the first part of our discussion on curl and divergence. Sadly, the topics of curl and divergence is where we will end our semester. But it does provide a nice transitional topic, in the sense that curl can be related to determining whether certain vector fields are conservative or not, and it can also be used to rewrite the right-hand side formula arising in Green's theorem, almost as kind of a precursor of what's to come in something called Stokes' theorem that many of you will encounter in future engineering courses. So to begin, we need a little bit of, we'll say, definitions or notation. So first we're going to start off with this upside down triangle, which we will refer to as del. And del is defined to be what we might think of as an operator. It is going to be a vector made up with entries partial of x, partial with respect to y, and partial with respect to z. And when I say it's an operator, what I'm indicating is that by itself it doesn't really have any meaning. But instead it's something that we need to somehow apply to another vector. And this leads us into the definition of curl. For a vector field f, with three dimensions, made up of component functions p, q, and r, we define the curl of f to simply be del crossed with f. And since it's been a little while since we've done cross products, remember we place the standard basis vectors I, j, and k across the top row. Then we place the entries of del, partial with respect to x, partial with respect to y, and partial with respect to z across the middle row. And across the bottom row we have the entries of the vector field f, and I'm going to suppress that x, y, z dependence and simply write p, q, r. And using shorthand notation for partial derivatives, this cross product becomes ry minus qz for the first entry. Then remember that pattern plus, minus, plus. So in that middle j entry, we would have the partial r sub x minus p sub z. And for the third k entry, we would have qx minus py. And now that we've introduced this new idea or concept, the curl of a vector field, let's evaluate a simple example. And this is a point where if we were in class meeting face to face, I would turn the floor over to you. So what I would suggest is pause the video, take maybe 2 or 3 minutes, and come up with the curl of this vector field. And at this point, if you have not paused the video and determined the curl, you should certainly do that. So the vector field written component-wise would have a first entry of xyz, no middle entry, and minus x squared y for that third or k entry. The curl of this vector field is defined to be del crossed with f. And just as a reminder to make sure we're all on the same page, when it comes to calculating this determinant, we really think of it as being 3 little 2x2 determinants to calculate. So in that first I entry, we cross off the row and the column containing I, and for that remaining 2x2 matrix, we calculate its determinant. So that would be the partial with respect to y of minus x squared y minus the partial with respect to z of 0. Then in the middle entry, we start off ahead of time with a minus sign, and we play the same game. We go to the j entry, we cross off the row and the column that we find j, and once we've crossed off the row and the column, that remaining 2x2, we calculate its determinant. So that would be the partial with respect to x of minus x squared y minus the partial with respect to z of xyz. And then similarly for the third, or k entry, we would have the partial with respect to x of 0 minus the partial with respect to y of x, y, and z. And to be honest, when it comes to calculating the curl of a vector field, really the most difficult aspect is the fact that it's just tedious. we have to write down all of the notation associated with calculating a cross product, and then just make sure we really keep track of all of these partials. So just working from left to right, we have minus x squared, minus the quantity minus 2xy minus xy. So note all those minuses will cancel, and then minus xz, which gives us a minus x squared 3xy minus xz. And the observation that I would make at this point is when it comes to computing the curl of a vector field, computationally, it's really not a difficult thing. As I mentioned, the most difficult part is really just going through the tedious aspects of the computation. So that leaves us with the question, why is this useful? We get back a vector. What does this vector tell us? Why are we interested in the curl? Well, one thing is going to be related to determining if a vector field is conservative, which we'll touch on the next page. But before moving on to explore that application, let me note that there's also a physical interpretation when we are calculating the curl of the velocity vector field for fluid flow. So if you are in this velocity vector field and you're sitting at a point, you can calculate the curl of the vector field at that point. And what the curl of the vector field will give you is a vector. And if there is some type of rotation occurring, this is the axis which you will rotate about. Furthermore, the magnitude of this curl vector is a measure of how quickly particles would rotate around that axis. So similar to the application we encountered in our cross product section in the beginning of the semester when we were dealing with torque and the tendency of a body to rotate about an axis, there's something here again with curl of a vector field and measuring how likely something is to rotate around the curl vector, which is an application that you may encounter in future courses. So let's go ahead and think about the relationship to conservative vector fields. Before diving directly into conservative vector fields, let me make just a quick reminder. So recall from earlier in this chapter, we defined that a vector field F is conservative if it is a gradient vector field. And when it came to determining if a vector field was conservative, we saw that it was very easy to check if a two-dimensional vector field was conservative. So if you have a two-dimensional vector field F equals PQ, we saw that this is conservative whenever you had a relationship satisfied by the partials. P sub y is equal to Q sub x. But if you go back over our notes and videos, you'll note we never mentioned anything related to a vector field with 3 entries in determining if it is conservative. And this is a spot where the curl is useful. And without going through any details, I want to very quickly and simply state this first property. The curl of a conservative vector field, so this is assuming it has 3 entries, turns out to be equal to the 0 vector. And this idea, it turns out, goes in both directions. If you were to know that you have a 3-dimensional vector field whose curl is the 0 vector, then I'm going to say under some reasonable restrictions. So it's not always true, but for us we will assume it's true. Then under some reasonable restrictions, which you can read in the book, then F is conservative. And this fills in quite a gap we had previously encountered. In order to apply the fundamental theorem of line integrals, we need to know a vector field is conservative. And we now have a way of determining if a 3-dimensional vector field is conservative. With this idea in mind, I would like you to pause the video and take no more than 2 or 3 minutes and determine, is this 3-dimensional vector field conservative? And hopefully at this point you've paused the video and you've came up with an answer. To get some details down, the curl of the vector field is defined to be this cross product. And to get the first entry in the cross product, we cover up the I column and the I row. And then for that remaining 2 by 2 determinant, we multiply down the main diagonal, subtract away what we get down the cross diagonal. So the partial with respect to y of minus y squared is minus 2y, and then we subtract away the partial with respect to z of xyz. And then there will be 2 more entries in the curl vector. But note at this point, we already know the answer. This is not equal to the 0 vector. The reason it's not equal to the 0 vector is because 2y minus xy is not always going to be 0. And we're done. So the conclusion would be that f is not conservative. And if you need a reason, it's because the curl of f is not equal to the 0 vector. And I'll throw in here as well that if you were to continue on and finish calculating it, you would get x and yz, and it's not bad practice to finish up the computation. I want to finish up our discussion on curl by just noting that there is a relationship between curl and Green's theorem. If we go back to the integral we have for Green's theorem, that tells us that a line integral of the form p dx plus q dy is equal to the double integral over region D of the partial dq dx minus dp dy. It turns out that this integral on the right, we can rewrite the quantity that we are integrating so that it involves the curl of a vector field. The vector field that it would involve is f is p, q, and we need 3 dimensions, so we'll say 0. And then I'll remind you that k is the vector 0, 0, 1. So what we are integrating is in fact the curl vector dotted with k. And this is not something we will encounter for the remainder of this semester, but it's worth mentioning in the sense that this is a transitional type topic, and if in a future course you encounter something called Stokes' theorem, this would be kind of the 2-dimensional version of Stokes' theorem. In the next video, we will focus in on the divergence of a vector field. So stay tuned and take care.